Yes, friends, welcome once again to the class. Yes, so we will start with maths optional our next lecture. If you have not watched the previous lectures, then kindly go to the pinned comment which is at the bottom, and in the description also the link is there, in the video description also, and in the form of pinned comment also there is a link. Just go on that link and start watching from the very first class, then you will understand everything. Okay, so question is, let A and B be two orthogonal matrices of same order. Suppose A and B are two orthogonal matrices which have the same order. Then determinant of A plus determinant of B equal to 0, and we have to also prove that A plus B is singular matrix. Okay, so A and B are orthogonal, it is given to us, and also it is given to us that determinant of A plus determinant of B equal to 0. These two things have been given to us. We have to prove that A plus B is singular matrix. What does it mean by A plus B is singular matrix? A plus B is singular matrix just means that determinant of A plus B is also equal to 0. Okay, so what we have to prove over here? We have to prove that determinant of A plus B equal to 0. So let A and B be two orthogonal matrices as written over here. We have to prove that A plus B is singular matrix. That is, we have to prove that determinant of A plus B is equal to 0. Okay, therefore since A and B are two orthogonal matrices, so by definition of orthogonal matrices, what is the definition of orthogonal matrices? If you have watched the previous classes, then you must know this, that orthogonal matrices are such matrices which satisfy this condition, that A transpose equal to A transpose A equal to identity matrix. Similarly, B is also orthogonal, so B transpose, product of B transpose, post product of B transpose with B, and pre product of B transpose with B, both yield you I. Okay, so these are your equation number 1 and 2 from definition of orthogonal matrices. Also, we know this very well, that as A and B are orthogonal, so that's why determinant of A will either be equal to +1 or equal to -1, and as B is also orthogonal, so determinant of B will be equal to either +1 or either -1. Okay, now the situation which is given to us in the question is that determinant of A plus determinant of B equal to 0. This is the situation which has been given to us in the question. So given is that determinant of A plus determinant of B equal to 0. Okay, so let us consider a situation of this kind, that determinant of A can be +1 or -1, determinant of B can be +1 or -1. So the addition of these two must be 0. The addition of determinant of A and determinant of B must be 0, but at the same time determinant of A should be either equal to +1 or -1, and determinant of B should also be either equal to +1 or either equal to -1, and at the same time determinant sum should also be 0. So only two situations are possible. Either determinant of A is +1, then determinant of B will be -1, and if determinant of A is -1, then determinant of B will be +1. Okay, so only two situations are there. Either this is -1, then this will be +1, and either if this is +1, then this will be -1. Okay, so you need not prove based on both this. Okay, you need not take two conditions, just take single condition, take only single condition. You need not take two conditions, because it will unnecessarily it will make the answer lengthy. It will make the answer lengthy. So as A and B are thus determinant of A +1 and determinant of B -1 is the only situation you should take. Okay, okay, so you took that situation, that determinant of A, let determinant of A equal to +1 and determinant of B equal to -1. You could have taken determinant of B equal to +1, this +1 and this -1. You could have taken this -1 and this +1 also, you could have taken, but the solution would be little bit different then. Okay, but as the situation is dicto the same, only in place of A there will be B, and in place of B there will be A in that case. Okay, and A and B are just arbitrary representations. Okay, if you take determinant of A equal to -1, then you are simply showing the B with symbol A, that's it. Okay, so there is no difference at all in both the situations, whether you take this as +1 or -1 and determinant of B equal to +1 or -1. There is no difference at all. Only difference will be the derivation which you are doing here. If you take the reverse thing, then what will happen? If you take, suppose this equal to -1 and this suppose you take +1, then what will happen? Instead of in the proof, instead of determinant of A over here, determinant of B will come. You will write determinant of B over here instead of determinant of A. All the other things are going to be the same. Okay, so determinant of A equal to +1 and determinant of B equal to -1 is the condition which we have taken. Now determinant of A plus B, okay, we have to find out this value and prove that this is equal to 0, because if determinant of A plus B if it is equal to 0, only then it will imply that A plus B is singular. Okay, so determinant of A plus B equal to determinant of A plus B into 1. 1 is the multiple of every number. So determinant of A plus B equal to determinant of A plus B into 1. Okay, then determinant of A plus B as it is, instead of 1 you will write determinant of A. Okay, as we have taken the condition over here. Okay, so the same condition I have written over here also. As the 1 is equal to determinant of A, so replace 1 by determinant of A. Then we know this very well, that determinant of A and determinant of A transpose are equal. So write this as it is and replace A with A transpose, because both are the same thing. The determinant of a transpose and the determinant of original matrix and its transpose are same. Determinant of original matrix and its transpose both are same. Okay, so determinant of A plus B into determinant of A transpose. Then you will take these together. Okay, determinant of A into, what is the property we have used here? Actually you must write one more property over here in the bracket. Okay, in the bracket you should write determinant of A into determinant of B is equal to your determinant of AB. This is the property you have used over here. Where? Here you have used this. This is one entity, this is another entity. Separately determinant has been written. So these two can be multiplied together and determinant can be written outside. So determinant of A plus B into A transpose. Then A transpose will go with A transpose will go with B. So determinant of A transpose plus B A transpose. This is by equation 1. Okay, A transpose equal to I is from equation 1. How? Because by the definition of orthogonal matrices. So determinant of I plus B A transpose. Then what happens? Instead of I, now we had written A transpose, right, and I. Now I will be replaced by BB transpose. So we replace BB transpose as BB transpose is equal to I from definition of orthogonal matrices, and as B is orthogonal, that's why. So BB transpose will be equal to I. So BB transpose plus BA transpose. Then determinant of, we will take B common from here. So I took B common from outside from here. And as soon as you take B common outside from there, you get B transpose plus A transpose remaining. Then what will you do? Then determinant of B into this thing. Then separate this and this. Okay, by using which property? The property you must write over here as determinant of AB is equal to determinant of A multiplied by determinant of B. Okay, This is the thing. So determinant of AB becomes determinant of A into determinant of B. So now we know this property that A transpose plus B transpose is equal to AB whole transpose. So B transpose plus A transpose, so AB whole transpose will be there. And now determinant of B is equal to -1, as we have already seen in the previous thing. Determinant of B is equal to -1, right? So instead of determinant of B, I wrote -1 over here. And A plus B whole transpose becomes equal to A plus B. Okay. So -1 into determinant of A plus B. So you know this very well that you started with determinant of A plus B, and now you have ended with minus determinant of A plus B. So what did you get from here? From here you got, what did you get from there? You got determinant of A plus B is equal to minus determinant of A plus B. Okay. So when you take it to the left hand side, what do you get? 2 times determinant of A plus B, that will be equal to your 0. So determinant of A plus B will come out to be equal to 0, right? So the same thing has been written over here. This minus will go here and it will become plus, those will get added. So determinant of A plus B equal to 0. So A plus B is your singular, hence proved from here. Okay, hence everything was proved from here. If suppose such a situation is there, if A matrix equal to alpha 1 beta 1 gamma 1, alpha 2 beta 2 gamma 2, alpha 3 beta 3 gamma 3, such a situation is there, suppose, and suppose this particular row satisfies this equation, alpha 1 square plus beta 1 square plus gamma 1 square equal to 1. Suppose this second row satisfies this condition, alpha 2 square plus beta 2 square plus gamma 2 square equal to 1. And suppose this third row satisfies this condition, that alpha 3 square plus beta 3 square plus gamma 3 square equal to 1. Okay. And suppose these two rows, first and second row, satisfies this condition, that alpha 1 alpha 2 plus beta 1 beta 2 plus gamma 1 gamma 2 equal to 0, alpha 1 alpha 2 beta 1 beta 2 plus gamma 2 gamma 1 gamma 2 equal to 0. Then this and this row satisfy this condition, that alpha 1 alpha 3 plus beta 1 beta 3 plus gamma 1 gamma 3 equal to 0. And this row satisfies this condition, that alpha 2 alpha 3 plus beta 2 beta 3 plus gamma 2 gamma 3 equal to 0. Then means the sum of the then A is orthogonal in such a situation, that is the sum of the squares of the elements of each row equal to 1. Okay, sum of the squares, okay. So you can see sum of the squares, okay, sum of the squares of the elements of each row, okay. So sum of the squares of the elements of each row equal to 1, sum of the products of the elements of each any two rows equal to 0. Okay, so sum of the products of elements of any two row is equal to 0. Sum of the products plus this, sum of the products of the elements of any two rows equal to 0. Okay, the sum of the products of the elements of any two rows equal to 0. So that implies that A is an orthogonal matrix in that condition. Okay, so such is the thing. So thank you very much. We will discuss from here in the next class. Okay, we will discuss from here onwards in the next class. Okay, so up to here done. I have marked also. Okay, I have marked also. Now we will do from here onwards. Start from here, I will write. Okay, from here onwards we will do in the next class. So thank you very much.